Hello and welcome to my next video on NMR. Now the basics. Now most of this you do not need to know. It's on just like double spread in the textbook, which they say you don't need to know most of it, but it just explains it. So I'm going to try and explain it. But I repeat, up until the chemical shift you do not need to know this. So NMR is nuclear magnetic resonance. And it's an analytical technique that's been used over the last 70 years to kind of determine the structure and shapes of molecules. Now, the ones we tend to use are carbon-13 and proton. Now, carbon-13, normally you have carbon-12, but you have an extra, well, because what you want an odd number of nucleons, which are neutrons and protons. So in protons you just have one proton, so you have an odd number. Now why do you want this? Well, protons and neutrons have a property called spin, which can be in one of two opposite directions, rather like electrons. So remember when you do electron configurations, you can have an arrow going up, arrow going down, because they spin in opposite directions. We can have that with protons and neutrons. In the nucleus, opposite spins pair up. So if you have 12 nucleons in a carbon, 6 of them will be up, 6 of them will be down, and they'll pair up. So one's up, one's down. Overall, it's not zero. That's why you need an odd number. So you've got one that has a kind of overall spin. So basically, these isotopes with an unpaired nucleon produces a small residual magnetic spin, generating a magnetic field. Now think of these like tiny magnets. When you then put these into a magnetic field, you'll get these magnets lining up in one of two directions, either with the field or against the field. Nuclei that oppose the magnetic field have a higher energy than those aligned with the magnetic field. The stronger the magnetic field, the larger the energy gap between these energies. Basically saying that spins that are aligned with the magnetic field have a lower energy level than those that oppose the magnetic field. Now, what you do is then you have something called resonance, which is when you essentially have a nucleus that's in its low energy spin state, and you can promote it to the upper energy spin state by providing energy that is exactly equal to the energy gap. This is excitation. So you essentially excite the nucleus, and you do this by supplying low energy radio frequency radiation, or radio waves. Then the excited nucleus will later drop back to its low energy ground state, emitting exactly the same amount of energy in the form of radiation. This is called relaxation. So what you do is you put in radio waves, it excites the nucleus, and later on it will drop back and release energy again in radiation form. Now this cycle of excitation and relaxation of the nucleus is called resonance. And resonance continues as long as the frequency of the radiation supplied has an energy that exactly matches the energy gap between the spin states. And this is how you get nuclear magnetic resonance. So next you need to look at nuclear shielding. Now, the magnetic field felt by a nucleus depends on two factors: the applied strong magnetic field and a weak magnetic field generated from electrons surrounding the nucleus and in nearby atoms. An atom's electrons will shield the nucleus from some of the applied magnetic field, and this is what nuclear shielding is. The extent of nuclear shielding depends on the electron density in nearby atoms or groups. This alters the environment of a nucleus, changing the energy gap. The result is the atoms in different environments have different resonance frequencies. That's the important thing. And now everything after this you need to know. But basically what that's saying is that if you have a bond that is electronegatively different, so let's say carbon and oxygen, the electrons are slightly more attracted to the oxygen, and that gives electron shielding. Now, you don't need to know about anything we've just done, it's just background. The stuff you do need to know is chemical shift. Chemical shift, which is shown as kind of delta, is the place in an NMR spectrum at which nucleus absorbs energy. NMR spectrum are calibrated using the delta scale, measuring units of part per million, or ppm. And basically we measure it relative to something called TMS, which is tetramethylsilane, which is silicon with 4 methyl groups. Why? Because it has the most amount of electron shielding. Because the silicon electrons has 4 groups, each 4 pairs of electrons. The electrons will go to each of the methyl groups of the carbon, and then in that carbon the electron pairs to the hydrogens will be pushed towards the hydrogen. So you have the most amount of shielding around the central atom. And that's what the basis is. We define this as a delta equals 0 ppm. And then we compare all the other chemical shifts against it. As I say, you won't even be questioned on this stuff, it's just good to know. And then you need to know about solvents we use. And we use something called deuterium, which is basically a hydrogen with a neutron and a proton. So it's got a mass number of 2. And why we use this is because it hasn't got an odd number, so it's going to produce it'll have no effect in the NMR machine. It won't do, overall spin or magnetic anything. And so we use solvents for proton and carbon NMR. We use something called CdCl3. Now normally you'd use CHCl3. So that's trichloromethane. But in this case we have a D instead of an H, so we have a non-odd numbered nucleused hydrogen. And then you can remove CdCl3 by evaporating it at the end. Now the important stuff is really from now on, because they won't ask you on the theory, they're going to really test you on how to do it. So carbon-13 NMR, we'll look at the spectrum. I've got 4 examples, but carbon-13 NMR can tell you 2 main things. It can tell you, it talks about carbon environments, that's why it's carbon. So the chemical shift tells you the type of environment, the number of peaks tell you the number of environments. So I'll give an example of propane. CH3, CH2, CH3. A carbon environment is just a different kind of way of looking at the molecule. So if you look at where I put the first one on the left, you have CH3. Now that's a carbon bonded to 3 hydrogens and is then bonded to a CH2, CH3 group. Now if you look at the other one, that is a carbon bonded to 3 hydrogens, then bonded to a CH2, CH3 group. So it's exactly the same environment. They're kind of identical because they're symmetrical. And then the middle one is a carbon bonded to 2 hydrogens and 2 CH3 groups. That's a different environment. So you have 2 environments overall. And the other thing is you might be given the integral. Now anyone who does maths knows that the integral shows the area under the curve. And what the integral does will show you the ratio of the number of environments. So if you have 1, 1, or in this case, if you had peaks, you would have a peak with an integral of 2 and a peak of an integral of 1, because there's 2 lots of one environment, 1 lot of the other, and there are 2 peaks. Yet again, it will become much clearer when I give an example. I'm going to show you how to do these as well. You're given a formula sheet with the chemical shifts on it. You just need to look at how many environments are there, what type of environment are they, and how many of each type of environment there are. Proton, this is when you look at hydrogens. Now this looks at hydrogen environments. So if you have CH3, you're looking at the hydrogens rather than the carbon. And it's very similar. The number of peaks equals the number of hydrogen environments. The chemical shift equals the type of hydrogen environment. The integral equals the ratio of each environment. Now, if you have CH3, that is 3 hydrogens on the same carbon. So those could be, they would count as different environments, as such that they are each individual, but they are all attached to a carbon which is then attached to the same stuff. So they are the same environment, just like with carbon, if it's attached to the same sort of carbons, it's the same environment. So the integral generally shows, rather than the ratio of hydrogen environments, it shows the ratio of the number of hydrogens. So if you had 3 to 2 to 2 to 3, you would have 3 hydrogens, 2 hydrogens, 2 hydrogens, and another 3 hydrogens. As I say, it'll make much more sense when we go through examples. But the other thing you have here is a splitting pattern. In carbon-13 NMR, you have just a peak, a straight peak. In proton, in NMR, you can have a single peak, a singlet, 2 peaks together, doublet, 3, triplet, 4, quartet, 5, quintet, 6, septet, all that. Or hextet, rather. And we have the rule called the n+1 rule, which means that if n basically equals the number of hydrogen on adjacent carbons, And the number of peaks there will be at that one point is one plus the number of hydrogens on adjacent carbons. So if you have a peak, if you have our CH3, CH2, CH3, on the CH3 there are 2 protons or hydrogens on the adjacent carbon, which means you would get a triplet as a splitting pattern. On the CH2 there are 6 hydrogens on the adjacent carbons, because you've got 3 on one side, 3 on the other, which means you would get a septet, or heptet, I think, sorry, heptet. Now, as you can see here, I've done 2 lines equals 1 hydrogen, 4 equals 3. Now the other thing is, if you get a singlet, 1 peak, it means there are no hydrogen, not a hydroxide group, but 0 hydrogen on the adjacent carbons. Another thing you need to know is D2O. Remember, D is the hydrogen with a neutron and a proton. When that's added, it will remove any peaks caused by OH and NH groups. There are no examples, but if it says, you know, what effect will D2O have on this NMR spectrum, any peak which has an O to H bond or an N to H bond will go. Right, I'm just going to give you some general tips about how to approach these questions, and then we'll look at examples. Always quote the shift and the type environment. So what I will do is I will always say, let's say in carbon, you will mention, you'll go, there is a peak at 220 ppm which shows this, and you draw the little kind of environment it shows. If it's in a proton one, I will say there is a quartet at this value which shows this type of environment, and you'll see how I answer it. Then you want to look at the integral ratio. That's the number of each type of environment. So 2 to 1 to 1 shows there's 2 of one environment, 1 of the other 2. And then look at the number of peaks. That shows you the number of environments. And if you're looking at proton, look at the splitting pattern and D2O and using the n+1 rule. Now, a tip, they might not tell you what sort of NMR spectrum you're looking at. But if you see a large scale from 0 to 220, you've got carbon. If you see one from up to just 12, you've got proton. As other things, little tips, in proton NMR, if the integral is bigger than 3, you have more than one type of that environment, because there's no way you can have 4 hydrogens on the adjacent carbon. You can have 3 as a CH3 group, but if you've got 4 or more, you must definitely have more than one environment, unless you get an integral of 5 or 6, most usually 5, because that will indicate a benzene group, because benzene have 5 hydrogens and generally an R group added on as well. So that's something else to look out for. It's really easy though to tell if it is a benzene, because benzenes have a very particular chemical shift. So they will tend to have like 5 peaks at about 7 ppm. And there's an example we'll see later. So now the important thing is examples. Now this first example is very easy. Now I've had to draw the ketone, but here are 3 ketones. And I want you to identify which one. And then ask you to identify the peak at 210. Now this question is a lot easier than you think, and it's really easy because look at the number of carbon environments in each of the ketones. In ketone 1, CH3 is 1, CH2 is another, CH2 is another, that carbon COO is 1, CH3 is another, because they all have different carbon chains added on. In ketone 2, you have a CH3 and a CH3. They're both the same environment because one CH3 is bonded to a CH, which is bonded to a CH3, and a CH is also bonded to a COO CH3. And the other CH3 is added to a CH, which is bonded to a CH3 and a COO. As you can see, they all kind of have that little bit of symmetry across there. So they're the same environment. So you only have 4 environments. In ketone 3, you also again have 5 environments. Now if you look at the NMR spectrum, there are only 4 peaks. There must be 4 environments, and one of the peaks, being about double the height, must be done twice. And the only one which has that kind of peak has 4 environments where one of them is doubled is ketone 2. So it must be ketone 2. And at 210 ppm, it must be the COO bond if you just look at your formula sheet. So that's a very easy question because you just need to count the number of environments. Next question is a slightly harder one. Now, this one I suggest you do. All I've done is just labelled 1, 2, 3, 4, 5 peaks, just so when I use the next slide you can reference it. But pause and have a go and see what you come up with. Right, good. Now, you've also got a mass spectrum here. I've done that at AS. The first thing you look at is where is the M plus peak, the furthest peak, and that's at 106, so you know that the MR is 106. Now also, you've been told it's an aromatic hydrocarbon, so it only contains carbon and hydrogen and must contain a benzene group. Now, to get a rough idea of how many stuff you have added to the group, I've done some little kind of cheaty methods here. A benzene ring itself is 78 MR, so I've done 106 minus 78 equals 28. 28 equals C2H4, which is an ethene group. Now, I can tell you now, it's not going to be a benzene plus an ethene. They're going to be bonded together in some way. But that's why I put roughly. While 28 does exactly equal C2H4, that's not how it's going to look when you add it to the benzene. So it said roughly. But basically, if you get C6H6 plus C2H4, you get C8H10, which works out to be 106 MR. So that we have the correct formula. And then just draw 4 isotopes. Well, if you just draw them, you can have 2 methyl groups on different places, and you can also have a C2H5 group. Now, it's quite hard to draw this, but we know that there are 5 carbon environments. So we're looking for the benzene one, which has 5 carbon environments. Now, the way you look at it here is the CH3 is 1 carbon environment. Then the carbon it's attached to is an environment. And as you see, all the dots indicate a carbon environment. So there are 1, 2, 3, 4. Because what you need to do is look for symmetry. And if you look in between the CH3 and the CH3, if you cut a line down, you've got symmetry. Which means all the carbons on the other side will also be exactly the same carbon environment. So the CH3 is exactly the same carbon environment as the other CH3. So the kind of weird bracket I've drawn around it shows that these environments are the same. So in something with C8H10, there are a possible number of 8 carbon environments. This one is exactly symmetrical right down the middle, so there are 4. The next one. Now, if you look at this one, it is also symmetrical down the middle, but this time, instead of being, in the straight line between CH3 and CH3, you can see the symmetry is slightly different, which means you have 1 on the CH3, 1 on the carbon it's connected to, 1 on that carbon, and then 1 at each point on the symmetry. Because if you think of something where you have symmetry, that line of symmetry, the points on the line of symmetry also count as a new carbon environment because they're not repeated. So you have 1, 2, 3, 4, 5. And then the other 3 are the same. So you have 5 carbon environments. On the next one, you have a CH3. You can see the line of symmetry is right down the middle. So you again only have 4. And on the C2H5, you have 2 carbon environments on the C2H5. 1 on what it's connected to and some of the others. And this time you're only missing out 2 that are the same. So there are 6 carbon environments, meaning overall there's only one that has 5 carbon environments. In the spectrum there are 5 carbon environments, so it must be the second one I've drawn. And it says, use spectra to identify the aromatic hydrocarbon and say why you've ruled out the other 3. The other 3 because they're not 5 carbon environments. I hope that makes sense. Yet again, reasonably hard to explain, but I hope that makes sense. Now, that's the carbon ones. They come up much less regularly. The proton ones will come up more. So again, I want you to do this and then do it first and then come to go through the answer. Good. So, now the best thing is about protons is that you're almost always guaranteed an ester. And it says here, it's an ester, so we know it's an ester. Now, if you look, first thing I've done is drawn the ratio of the integrals. 5 to 2 to 2 to 3, so we know there are 12 hydrogens, which is fair enough. Now, we also know that there are 4 hydrogen environments because there are 4 peaks. So I've just labelled them. Now I'm going to write down the different groups. So at number 1, so this is kind of going from left to right, on hydrogen environment number 1, there's a hextet. Just let you know, they will allow a quintet and a heptet because it's a bit unclear, but I've said a hextet at 7.3 ppm. This indicates, if you look at your data sheet, a benzene ring with an R group added onto it somewhere. So there's an R group added on. Now the integral equals 5, which means there are 5 hydrogens, which you would expect if you have an R group. So that's fine, we get that. Now we don't really need to worry about the splitting pattern here. And it's kind of obvious why if you look at it, how with benzene rings splitting pattern doesn't work quite as well. On number 2, we have a triplet at 4.4 ppm, so I've quoted the splitting pattern and the chemical shift. That indicates an RCH2O group. Now remember, in an ester you have a C to O to a carbon with a double O bond on it, so we know there must be a C to O bond. And why I said it's CH2, because it could have been CH3, could have been RCH2 or R2CH. Now why, or even R3CO. Now why, no, it has to be, no, it can't be that actually, ignore me. Now why I said it's CH2 is because the integral is 2, meaning there are 2 hydrogens, so CH2 must be the one. And because there's a triplet, n+1 rule means that there must be 2 hydrogens on the adjacent carbon. On number 3, you have a triplet at 2.8 ppm. This indicates a CH2 connected to a benzene. We know it's a CH2 because the integral is 2, so it must therefore equal 2 protons. Since it's a triplet, there are 2 protons on the or hydrogens on the adjacent carbon. And finally, you've got a singlet at 2.2. Now this indicates at 2.2 a carbon with hydrogens on it connected to a carbon with a double O bond connected to an R group. Now I know it's an H3 because there is an integral of 3, meaning there are 3 hydrogens. It's a singlet, so there are 0 hydrogens on an adjacent carbon, which means it is a CH3 group. So you can now start pairing these together. You know there's an H3C to COO group. Now since it's an ester, the R must be an O. You know the O is connected to a CH2. And then at the end you know there is a benzene connected to a CH2. So those 2 CH2s probably connect together to form this. Now I hope you got that, but as you can see I've labelled the environments. The benzene is number 1, CH2 connected to it is number 3, the CH2 connected to the O is number 2, and the CH3 at the end is number 4. So compare that and hopefully you got it right. And the final example is another proton one, but this one has some extra stuff on it because it has a mass spec and chemical analysis using percentages, which is an AS thing, so I hope you remember. So I'll give you some time to do that, pause and do it, and then come back. Good. So we start off with the easy bit. Elemental analysis by mass. Now this is, you assume the percentage is the mass, divide it by the MR to get the moles, divide the moles by the smallest moles, in this case oxygen, you get ratio 4 to 8 to 1. So we've got C4H8O. Work out the MR of that, it's 72. Now we know by the mass spectrum the MR is actually 144. 144 divided by 72 equals 2. So therefore we know that the chemical has the molecular mass C8H16O2. And that means we can probably guess it's either going to be a carboxylic acid or an ester. And I don't think they've told us. So it's going to be a carboxylic acid or an ester because it's got the O2. Or it could be a dialcohol. So, then what? Now, first step, we look at the integral signs. So we got 2 to 2 to 3 to 9, there are 16 hydrogens. Now we know from our molecular formula there are 16, so that works. 4 peaks, 4 hydrogen environments. Now one thing I can tell you already is that there is an integral of 9, meaning there's 9 hydrogens in one environment. So we are guaranteed to have more than one environment. And we'll see which one it is right at the end. Peak 1 though, that's a quartet at 4.2 ppm. Now this indicates an RH2C to O group, so it's basically a CO group. And we know it's H2 because the integral is 2, so it must be 2H. It's a quartet, so there are 3 hydrogens on an adjacent carbon. Now there's a singlet at 2.3 ppm, which shows RH2 carbon with a COO bond. Integral again equals 2, so it must be 2 hydrogens. It's a singlet, so there are no hydrogens on adjacent carbons. So this is good. Now looking at the first 2 we've already got, we know we've got an ester. So we've got an RH2C to O group, which will then be bonded to the carbon double O to a carbon H2R group. Now the interesting thing is we've got a CH2 group and then there's a further R group, which must be a carbon, because we know that's all there is now, because we've done the oxygens, must be a carbon. Yet there are 0 hydrogens bonded to it, so that's interesting. We'll see that at the end. Triplet, number 3. Triplet at 1.3 ppm indicates a CH3 bond. Integral equals 3, so we know it's CH3. 2 hydrogens on the adjacent carbon, so we can be pretty sure it's probably CH3, CH2. And finally, the interesting one, there's a singlet at 0.9. Now, at 0.9 it indicates an RCH3 bond, but since it's got 9, there are 9 hydrogens, so you've got pretty sure it's a CH3 bond 3 times. So you've got a carbon connected to 3 lots of CH3, which will then be connected to that CH2, which has 0 hydrogens on the adjacent carbon. That's how you have it, because it's CH2 connected to a carbon, which is then connected to 3 CH3 groups. So that carbon next to the CH2 has no hydrogens on it. This one equally has no hydrogens on it because the CH3 is connected to a solitary carbon which has 4 non-hydrogen groups connected to it. So we know we have 3 CH3 groups connected to a carbon, connected to a CH2, connected to a COO, connected to an O, connected to a CH2, connected to a CH3. If you just piece them all together. So you should get it looking something like this. As you can see, CH3 is number 3, CH2 is number 1, next CH2 is number 2, and all 3 CH3s are environment number 4. So that's the molecule you should have got. And that was a reasonably tricky one. So I hope that makes sense. And that's that. So conclusion now. Conclusion is literally there's carbon-13 NMR and proton NMR. Now, the best way to do this is just practice and do examples. I did 4 examples, all from past exam papers. So I think there are 2 or 3 more examples in there. If you do the ones in the book as well, there's some good ones in there. Find them online. Just practice. If you didn't understand anything, please ask and I will go through it. Again, via email or on my my live streaming session tomorrow, the Saturday 12th at 6 PM. And like, comment. I basically just hope this is probably the most confusing topic in Unit 4 chemistry. So I hope this made sense and you understood it a bit better now, because I know it does trick people up and a few people have asked for this video. So I hope that makes sense. Remember, you don't need to know about the first stuff about how NMR actually works. You're going to be given a spectrum and asked to work from it, or do something with the structure of molecules and spectrum. You're not going to be asked the theory behind it, or if you are, very little. Perhaps the only stuff they'll ask theory on is D2O. So I hope that makes sense, and goodbye.